All right, let's dive right into this explainer. Today, we're taking a task that honestly gets a bad rep as tedious admin work, and we're going to flip it into your ultimate construction superpower. We are decoding the bar bending schedule, or BBS. If you're involved in building anything, from a residential home all the way up to a massive skyscraper, grasping the mechanics of the BBS is absolutely crucial for structural integrity, efficiency, and major cost savings.
Just to set the stage for a second, imagine the sheer financial disaster on a massive 30-story commercial tower if you overordered a material that literally eats up a huge chunk of your budget. Or, even worse, what if you ordered too little or cut it to the wrong sizes and ended up halting construction entirely?
Yep, we're talking about reinforcement steel. It's crazy, but that hidden steel buried inside the concrete makes up roughly 25% of an entire project's cost. Getting those calculations exactly right, down to the literal millimeter, is what we are exploring today.
So, here's our roadmap for today. We'll look at the hidden steel skeleton, decode the BBS, walk through prepping your schedule, break down the magic of the 0.42D formula, and finally go over some seriously costly mistakes you need to avoid. Let's get right into it. Part 1. The hidden steel skeleton, the literal foundation of modern construction. Now, we all know concrete is fantastic. It's incredibly strong under compression, but it's also super brittle under tension. So think of steel reinforcement as a hidden skeleton, providing the ductility and tensile strength needed to hold that brittle concrete body together under immense stress. If the steel is the skeleton, then the bar bending schedule is the exact DNA code that tells that skeleton how to form, where to bend, and how to connect.
Moving to part 2, decoding the BBS and translating those blueprints into reality. So, how exactly do we write out this DNA code?
Well, a bar bending schedule, or BBS, is basically a highly detailed set of instructions. It gives the exact specs for fabricators and site contractors to accurately cut, bend, and place the rebar perfectly according to the structural design. Without it, you're essentially just guessing at the skeleton of your building.
And this is what it looks like. A standard BBS is just a meticulously organized table. You've got the bar mark acting as a unique ID, the diameter of the steel, your precise cutting lengths, quantities, bend shapes, and total weights. By using a system like this, steel stocks are managed flawlessly, making sure you have zero deficiency and zero surplus lying around on site.
Now, before we jump into the heavier math, we need to clear up a few foundational terms you're going to see everywhere in these schedules. Take development length, or LD, for example. That's the extra length of rebar that has to be deeply embedded into the concrete. It guarantees the rebar can actually transfer its massive structural loads into the surrounding concrete without just slipping out under pressure.
But why does all this hyper-meticulous detailing even matter? Well, let's look at a real-world scenario. On a recent 30-story commercial tower, properly running a BBS didn't just tidy up the site. It actually slashed overall construction time by a whopping 15%. Plus, calculating exact cutting lengths cut steel waste by 10%. When steel is 25% of your entire budget, a 10% drop in waste is a massive, immediate financial win.
Okay, part 3. Preparing your schedule step by step for maximum accuracy. We know it saves a ton of money, so let's actually walk through how to put one together.
It helps to think of this almost like a recipe. Step 1, you identify your structural members, your slabs, beams, columns, straight from the engineering drawings. Step 2, you count the bars needed based on your spacing rules. Step 3, you calculate your cutting lengths, which means taking the straight length and factoring in any hooks, bends, or development lengths. And finally, step 4, you calculate the total weight of the steel so you can confidently order it from your supplier.
Now, the real secret sauce for step 4 is this simple golden rule formula. When you need the unit weight of a steel bar in kilograms per meter, you just take the bar's diameter in millimeters, square it, and divide by 162. D squared over 162. It's a formula pretty much every site engineer knows by heart. Probably mutters it in their sleep at this point.
Let's see how that math actually plays out in the real world. An 8mm bar comes in at roughly 0.395 kilograms per meter. Step up to a 16mm bar, and it's much heavier, right around 1.58 kilos per meter. Using this golden rule lets site engineers instantly convert those lengths they mapped out in Step 3 into incredibly precise procurement weights.
Which brings us to part 4, the magic of 0.42D and deriving the crank length. Get ready, because we're about to decode one of the most famous, and honestly, sometimes most confusing, mysteries in civil engineering. First off, why do we even bend bars like this in the first place? Well, concrete members, like long slabs or beams, are constantly under tensile stress.
At the supports, you get these nasty negative bending moments. To fight those specific forces, we use cranked bars, also known as bent-up bars, that are angled upwards, usually at exactly 45 degrees. That shifts the steel right to where the tension is highest.
To figure out the cutting length of that bent, inclined portion, we have to lean on a little bit of geometry. So, visualize an isosceles right-angled triangle in your head. The vertical height, let's just call it d, is the center-to-center distance between the top and bottom main bars. Because the bend is exactly 45 degrees, the horizontal base of this triangle is also exactly equal to d.
Now we need the hypotenuse because that's the actual length of the angled steel bar. Remember the Pythagorean theorem? The square root of d squared plus d squared equals the square root of 2 times d squared? Let that math breathe for just a second. It calculates out perfectly to 1.414 times d. So the total length of that slanted piece of steel is 1.414 d. And right here is the brilliant aha moment. When a site engineer calculates the total length of a steel bar, they usually start by just measuring the straight horizontal span across the room. But that straight span already includes the horizontal base of our triangle, which is 1d. So, to figure out how much extra steel we actually need for the slant, we take our inclined length of 1.414d and just subtract the 1d we already counted. That leaves us with an extra 0.414d, which is practically rounded to the magical 0.42d. And that is exactly why you simply add 0.42d for every single crank in your bar.
All right, part 5, costly mistakes to avoid, from blueprint to disaster. Because while the math on paper is elegant, real-world application can be pretty unforgiving.
The journey from a blueprint to a finished building is absolutely loaded with pitfalls. Just a minor math error in calculating your lengths, that can literally render tons of steel entirely useless. Or what about ignoring standardized tolerances, like the IS 2502 standards? That usually means your perfectly calculated steel simply will not fit into the formwork. And a really huge one is failing to coordinate with your MEP folks, your mechanical, electrical, and plumbing teams. If your complex steel webbing ends up blocking a major plumbing pipe, you are looking at massive structural clashes and terrifying financial blowouts trying to fix it on site.
Honestly, this sheer level of complexity is exactly why the whole industry is moving away from manual, error-prone spreadsheets. Automated BDS software is the future, and it is a total breath of fresh air. These tools pull directly from the structural blueprints, flawlessly calculate those complex shapes, apply the correct bending rules, and instantly adapt if the architect decides to change the design.
So that leaves us with a pretty fascinating question to ponder as we wrap up this explainer. As our digital tools keep getting smarter, completely removing human error from these massive mathematical puzzles, how much more ambitious, cost-effective, and deeply safe will the steel skeletons of our future cities become? The bar bending schedule might be totally invisible when a building is finished, but it's undeniably the foundation of our modern world. Thanks for joining me to decode it.